This conference will now be recorded.
Good morning, students. In today's class, we are going to discuss about EMF equation of transformer. Students, are you clear my voice?
Yes, sir.
Right. So last class we discussed the construction, right? So due to some problems, it is not clear the explanation. So the topic we will discuss in today's class. Okay, now after that we go for EMF equation. Students, listen carefully. If you understand this, then only you can go through about that remaining topics. Right. Already we've seen that construction of transformer, right? So if you've seen that the diagram of transformer, it has the two parts. One is coils and core. So in that coil, how it should be connecting, and so based on that, it is classified as a core type and shell type. So, first of all, you have to know that what is the difference between core type and shell type, right? So then only you can understand that what is the difference between core type, shell type in the point of construction. So that is the thing you have to know that. See here, the transformer has two inductive coils. These are electrically separated but linked through a common magnetic current circuit. See, if you want to write any point, any information regarding transformer, you have to write this point. The transformer has two coils, and these two coils electrically isolated and magnetically coupled. So let me see how it will be. So I will draw that diagram, then you can understand that. See here, this is the diagram of transformer. This is the primary and it is the secondary. If you observe that primary and secondary, there is no physical contact between these two. So that's why the transformer has the two windings, and these two windings are electrically isolated. Electrically isolated means, so when the current will be forming, when the two contacts are connected. So but here these two windings are not connected, but these two primary and secondary windings are coupled through a magnetic field. So this is the point you have to write. The transformer has two coils, and these two coils are electrically isolated and magnetically coupled. Okay. Right. These two coils have high mutual induction. So that's why I already told you that every electrical machine, it may be motor and generator, transformer, these machines are working as a Faraday's law of electromagnetic induction. So which device should be generate the flux due to the current, that device should be capable to carry that Faraday's law electromagnetic induction. But here it is different, so we can call as Faraday's law of electromagnetic mutual induction. So mutual induction, why it is called as mutual induction means, suppose if you see this primary and secondary, now we are applying the input voltage here, but this, due to this voltage, the current will be flow through the primary winding, and this current makes to produce the flux, and this flux is coupled to the secondary. So that's why this works, the transform works on Faraday's law of electromagnetic mutual induction, and remaining generator and motor should be working on Faraday's law of electromagnetic induction. So that is the difference between a motor, generator and transformer. Here one of the two coils is connected to the alternate winding, so that is the input coil. This coil in which electrical energy is fed with the help of source called primary winding. It means that which the winding should we have to give the input voltage, that winding we call as primary winding, and the remaining winding, the secondary winding, is used to connect to the load. So you have to write about this transformer while starting the question. So these 4 points are very important. You have to mention these 4 points. The first point is it has the two coils, and these two coils are electrically isolated and magnetically coupled. And second thing is the transformer should be working on Faraday's law of electromagnetic induction, mutual induction, and the remaining 2 points are, one is for primary, another point is secondary. So primary means we are giving that input voltage to the primary and connecting load to the secondary. So these are the 4 points you have to write about the transformer. Now let us see the remain. The primary and secondary wind coil wound on a ferromagnetic metal core. So what is the why we are using the ferromagnetic metal core means, here the core is made up of silicon steel or cast iron. These two metals are belongs to the ferromagnetic material. So ferromagnetic material means when the current is flow through the coil, the core, then it carries the flux from one circuit to another circuit. So this is the behavior consists of a ferromagnetic material. Generally, the material we are using to construct the core is silicon steel or cast iron. These two metals are belongs to that ferromagnetic material. Okay, and the function of core is to transfer that changing magnetic flux from primary coil to secondary coil. So why this term is came means, generally we are applying that AC voltage to the primary transformer. The AC voltage should be like this. This is the sinusoidal supply, and due to the voltage, the current is carried by the primary winding. It is also in the form of sinusoidal waveform, and the flux due to the current, it is also in the form of sinusoidal waveform. That's why the core is transfer the changing magnetic flux. Changing means at starting it should be 0. After some time it goes to maximum, then 0, then negative. And so this is keep on going to the changing this value. And the primary has n1 number of turns and secondary has n2 number of turns. And this number of turns act as a vital role to the function of transformer. Why? Because if we already I told you that the transformer is classified based on the voltage levels. One is step up transformer, another one is step down transformer. Whether it is step up or step down, it is completely based on the number of turns. Suppose we have two number of turns, one is n1 and n2. When n1 is greater than n2, what type of transformer it is? Step up or step down? Right. Step down transformer. When n1 is less than n2, then it is called a step up transformer. So you can clearly say that based on the number of windings on the primary and secondary, we can simply say that it is step up or step down. So that's why the number of turns act as vital role in the function of transformer. Okay na? Right. So this is about basic of transformer. So you have to know basics about regarding the transformer. So regarding transformer means, what is the transformer, what is the parts having the transformer, how it will be working, like that. Right. Now let us see that working principle. The transformer works in the principle of mutual induction. Already I told you that the principle of mutual induction state that when the two coils are inductively coupled. So here inductively coupled means these two coils are connected through the flux. So that's why we call it as inductively coupled. And if the current in the coil change uniformly, then EMF induced in the other coils. This EMF can drive a current when a closed path is provided to it. So this is the working principle of transformer. See, these are regarding that how the flux will be transferring from primary to secondary. See, when the alternating current flows in the primary coils, a changing magnetic flux is generated around the primary coil. So when the voltage we can apply the primary, and this voltage tends to the move of current I, this current will be generated flux. This flux will go through the secondary winding through the core. And so you can simply say that how the EMF will be induced in the coil is E is equals to N into d pi by dt. So why I am giving the differentiation flux for flux alone means, here the number of turns is a constant and the flux is keep on going to change with respect to the time. That's why E is equals to N into d pi by dt. And this induced EMF depends on that how many number of turns having in the primary as well as secondary coil. and based on the number of turns, the EMF will be induced. Right. So now if a load is connected to the secondary winding, this EMF drives a current through it. Say already told you that the current is always flow through that closed loop. Suppose if you are not connecting the load here, it is open circuit, right? So the current should not flow in the open circuit. So when the load is connected here, then it makes a closed path, then I2 will be flowing. See here, the frequency of mutually induced EMF as same as that of alternating source which supply to the primary. So it means that the frequency of EMF and supply voltage both are same. That's why the frequency of transformer is always 50 hertz frequency. So while doing the problems, sometimes they will mention the frequency value in question, or sometimes they won't mention. So we have to consider as a frequency F is equals to 50 hertz. Right. Now we'll see the transformer construction. So these are the main parts of construction. One is core, primary winding, secondary winding, and the number of turns in the primary we call as primary number of turns, and the number of turns in the secondary we call as secondary number of turns. Now you are seeing the diagram like this, right? Now let me see what about transformer it is, step up or step down?
Step down transformer, sir.
Right, because the number of turns in the primary is more when compared to the number of turns in the secondary. So based on that, it is simply says that it is whether it is step up or step down. Now, what are the components we need to discuss in the construction point of view? The first thing is core. So what type of core it is, or what is the type of material we can use for core construction, and how the windings are providing on the core. So these are the topics we are going to discuss in the construction. Right. We'll see that what are the main two basic parts of transformer. The first one is magnetic core and windings. These are the two parts. One is core and then one is coils. Now magnetic core. The core of the transformer is either square or rectangular type in size. So square in the sense four sides are equal. Rectangle means two sides are equal and two sides are unequal. So this is the difference square and rectangle. So square shape we can use for that core type transformer. Rectangular shape we can use for shell type transformer. It is further divided into two parts, vertical and horizontal. Vertical in the sense, if you are using the core for three phase, you can mention like this. So this is the vertical shape. And if you are using the shell type transformer, it is in the form of horizontal shape. Now the vertical portion on which the coils are wound called limb, while horizontal portion called yoke. So this is the difference. Now the core is made up of laminated construction to reduce the eddy current losses. This is the main purpose why we are using the construction of core in laminated shape, is to reduce the eddy current losses. And generally high grade silicon steel lamination, and this thickness is 0.3 to 0.5 mm. So for large shades we are using the silicon steel. For small scale we can use cast iron. Okay, and the thickness of one plate is 0.3 mm to 0.5 mm are used. So this is the scaling we are using the core construction of a transformer. Right. Now we will see the winding. Generally we are using that two types of winding in the electrical system. One is copper wire and another one is aluminum wire. Now the conducting material is used in the winding of transformer. So why we are using the conducting material here? Do you know that? Conducting material and inducting material means, so when we call it as conducting material means when there is no changing in the losses and there is no losses, there is no changing in the parameters. అంటే మన స్టార్టింగ్ ఎంత కరెంట్ వేస్తే ఇస్తామో ఎండింగ్ కూడా అదే కరెంట్ వచ్చినాం, స్టార్టింగ్ ఎంత వోల్టేజ్ ఇస్తామో ఎండింగ్ కూడా అదే వోల్టేజ్ ఇస్తాం. సో there is no losses. That type of winding we can call as conducting material. The coils are used or wound on the limbs and insulated from each other. So how it will means, this is the core, right? Core shape transformer. and this is this leg is called as limb, and this is another limb. Here in this limb we are providing the primary winding, and in this limb we are providing secondary winding. While winding itself, we are providing the insulation of the type of the material winding. Why? Because the physical contact we can avoid by using the insulation. If we are not using the insulation here, then it causes the short circuit, right? So that's why first of all, here you can use the, you can see this brown color wire, right? After above this wire they are providing the insulation paper, like the whatever it may be, so to avoid the short circuit. See here, to reduce the leakage flux, it is necessary that the winding should be very close to each other to have high mutual induction. So this is the reason, while winding of the core, they are providing that very closely because of to reduce the leakage flux and providing the high mutual induction. So these are the 2 points you have to remember regarding that winding. One is while winding on the limb, we have to provide the insulation on the core to avoid the short circuit. At the same time, this winding should be very near to close to each other to reduce the leakage flux and maintain that mutual induction. Right. So this is the core type transformer. Here you can see this in the core type transformer we have 2 limbs. One is on one limb we are providing that primary winding, and another one is we are providing that secondary winding. So this is the structure of core. And so here for where we, so at what condition we can use sufficient to use the core type means for large size. For large size core type transformer, round or circular cylindrical coils are used. These circular cylindrical coils are very having the mechanical strength. And here what are the insulating materials we can use means, the first one is paper, cloth, mica, and etc. And there are some there is some air gap between these proceeding windings to providing the cooling ducts. Cooling ducts in sense for providing the cooling purpose. And this one is shell type transformer. Now the shell type transformer, we can provide the windings on the internal limb. So we have the 3 limbs, right? Limb 1. So these 2 are outer limbs and it is an inner limb, central limb. So sometimes we can call it a central limb. So here in core type we are providing that winding on the outer limbs, and here we are providing the central limb. So primary and secondary both are providing the central limb, but we have to decide whether we are providing the secondary at first or primary. So based on the voltage levels, if the primary is low voltage winding, then first we have to provide the primary winding, then insulation, then secondary winding. So it is sees that the low voltage winding should be provided first, after that high voltage winding. In a transformer, one winding should be low voltage or high voltage. So first of all we have to provide low voltage winding, after that insulation, then we can provide that high voltage winding. While providing these windings, we need to avoid that gap between the windings. Then only we can provide that mechanical strength, that is magnetic strength of the core. Right. Now we will see that EMF equation of transformer. Here the EMF equation is depends on that 3 parameters. What are 3 parameters means? The number of turns in the primary as well as secondary, frequency, and maximum flux. These are the 3 parameters mainly used to depends on the EMF equation. So E, we can simply that E is directly proportional to N into d pi by dt. So here N number of turns, pi flux, and T. So here T is referring to the frequency. Already you know the relation between the time and frequency, right? T is inversely proportional to the frequency. Now we need to derive the EMF equation for the maximum condition. So let me see that what is the maximum condition here. Now the flux generated in the transformer, it is in the form of sinusoidal waveform. This is the waveform for the flux. Now from here to here it will take that half of the time period T by 2, right? From half cycle from here to here. What about here? What is the time taken from 0 to here? So this is the maximum value. Pi m we can represent pi m. What is the time period taken from 0 to here?
T by 4.
Right, T by 4 because it is quarter cycle. Now this T by 4, how we can represent in the form of frequency? How we can represent T by 4 in terms of frequency? So already you know that T is equal to 1 by F, right? So this can be represented in the form of frequency is 1 divided by 4F, and the meaning ఏంటంటే మనకు maximum flux రావడానికి ఇంత టైం పడుతుంది 1 by 4F అని. ఓకేనా? So by using this notation we need to derive that EMF equation. So before that we will see that what are the parameters are involving in that EMF equation. Let N1 is the number of turns in the primary, N2 is the number of turns in the secondary, pi m, that is maximum flux in the core in Webers. So this is the point we need to find that EMF equation, maximum flux, and this maximum flux should be depends on that what is the maximum flux density of the core and what is the area of the winding. So these two parameters we can represent pi m is equals to Bm into A, maximum flux density and area of the. And next one is frequency of AC in input hertz. So it is always equals to 50 hertz. Now the flux increases from its zero value to maximum value pi m in 1 quarter cycle. It means that for obtaining the maximum flux it will take that 1 quarter, that is quarter means T by 4. So we can represent in the form of 1 by 4F second. అంటే ఫ్రీక్వెన్సీ ఫ్లక్స్ అనేది 0 నుంచి మాక్సిమం వెళ్ళడానికి ఇంత టైం తీసుకుంటుంది. సో దట్స్ వై we can represent, so we have the formula, right? E is equals to n into d pi by dt, right? So here how we can represent means E is equals to n into what is the time change. So d pi means changing the flux, so changing flux is pi m, and what is the time to take in this 1 by 4F. Okay na? So you can write E is equals to, so keep n is a constant, 4F into pi m. This is the initial EMF equation for the transformer. Next, see here. The average rate of change of flux is given by 4F pi m. So you can rate of change of flux we can represent like this, d pi by dt. So d pi by dt means d pi is pi m and dt is 1 by 4F. So you can simply write this 4F pi m. So this is the equation we obtained here. Now the rate of change of flux per turn means the induced EMF involves. So we can represent, this is the value 4F pi m volts. Now every sinusoidal waveform, it may be voltage, current or power, we can talk about this sinusoidal parameter, that is average value, peak value, RMS value, form factor. So these are the terms which is related to that sinusoidal waveform. But here if the flux is very sinusoidally, then RMS value of induced EMF is obtained by multiplying that average value with form factor. Already we have the formula for form factor is RMS value divided by average value, and its constant value is 1.11. But we need the value of RMS value. So if you want to RMS value, you have to multiply that form factor into average value. So you can write RMS value is equals to 1.11 into average value. Average value, what is the value of average? 4F pi m. So finally you will get the average value, the RMS value of induced EMF, we can write 4.44 F pi m. Now by this equation, what is the induced EMF in the primary, what is the induced EMF secondary? So we can simply represent it as capital E1. So E1 is equals to 4.44 F pi m N1. And similarly, the induced EMF in the secondary, we can write E2 equals to 4.44 F pi m and N2. This is the EMF equation of transformer with respect to the primary as well as secondary. Right. See here, the RMS value of EMF per turn we obtained that 4.44 F pi m. Now the EMF in the primary turns we can represent 4.44 F N1 into pi m. So instead of pi m we can represent Bm into A. Similarly for equation for secondary induced EMF V2. These are the two important equations for that EMF equation of a transformer. Now based on these equations we can find that transformation ratio. Transformation ratio means, suppose if you have the primary winding is 115 volts and secondary winding is 130 volts to 230 volts. Now its ratio is 1:2. Now what is the meaning of transformation ratio means? So we have the primary on one, primary side 1, and when it goes transfer to the secondary it becomes to the 2. Okay now? So the transformation ratio is generated by K and it is given by V2 divided by V1. So we will get 2. It means that the ratio should be transferred from 1 to 2. So this is the value it will decide. Now the transformation ratio we can represent in terms of voltage is V2 divided by V1. In terms of induced EMF we can represent E2 divided by E1. And in terms of number of turns, N2 divided by N1. And in terms of current we can represent I1 divided by I2. Now these three parameters are similar but current is different. Why? Because in transformer when voltage is high current will be low. When voltage is low current will be high. That is the difference happening in this transformer. Yeah, when voltage will be high and current will be low, and when voltage will be low current will be high. So that's why these two parameters are interlinked to each other. So we are representing that the power of transformer in terms of kilovolt and kVA rating. But in the case of generator and motor we can represent kilowatts. But the transformer alone we can represent its power in terms of volt and ampere. The reason is we have two losses in the transformer. One is iron losses, another one is copper losses. The iron losses is completely based on that voltage. How much of voltage we are obtaining, that much of iron losses we can obtain. But the current is used based on that copper losses, because the copper loss formula is I square R, right? When the I current will be increases, copper loss also increases. So that's why the losses in the transformer is mainly depends on that voltage as well as current. That's why the power rating of transformer is always represented that kVA. So this is the most important question for 2 marks. Why transformer rating is referenced in the kVA? So you have to write like this. In transformer there are two main losses will be occur. One is iron losses, another one is copper losses. Here the iron losses should be based on that the voltage available on the transformer, and the copper losses is based on the current. That's why due to this reason the transformer should be mentioned and rating in terms of kVA. Now let me solve two problems on the EMF equation. So just note down that the equation here. Example 1. First of all, write on the question number 1. See here, the maximum flux density in the core of a 250 bar 3000. So when the representation like this in the form of ratio 1:2, 2/3 like this value represents that primary voltage. So V1 is equals to 250 volts, and the 3000 represents that secondary voltage V2 equals to 3000 volts. You have to remember like this. So if the value is mentioned like this, we have the numerator values belongs to the primary voltage, the denominator values represent that secondary voltage. Frequency is 50 Hz. And the maximum flux density in the core of a 250 bar 3000 volts 50 Hz single phase transformer is 1.2 Weber per meter square. What is the how we can append this? How we can notate Weber per meter square? Which unit it is? 1.2 Weber per meter square అనేది ఫ్లక్స్ కోసందా మాక్సిమం ఫ్లక్స్ డెన్సిటీ కోసందా?
Maximum flux density.
Right. So the maximum flux density is 1.2 Weber per meter square. Okay. Now if the EMF per turn is 8 volts, determine primary and secondary number of turns, area of the core. So these are the readings, and remember one thing, the primary voltage is always equal to that primary induced EMF. This is the condition you have to remember. The primary supply voltage is always equal to that primary induced EMF. Now, based on this given parameters, we have to find that primary and secondary number of turns. First of all, E1, you can write E1 is equals to N1 into EMF per turn. Okay now, so EMF per turn means, so here we need to find that number of turns. Number of turns you have to find that. So first of all, note down that what are the parameters they given here. So E1 is equals to N1 into what is the value of EMF per turn? 8. Now we need to find the N1 value. So N1 is equals to E1 divided by 8. What is the value of N1? So here E1 is, what is the value? 250. Why? Because primary voltage is equals to primary induced EMF. 250 divided by 8. What is the value of N1? 250 divided by 8.
31.2.
So 31 pi. So I have to represent in terms of round figure 32. Okay now. So now we know the value of N1. Now we need to find that N2. So N1 is 32 turns and we need to find the N2. So here we can find the number of turns by using that transformation ratio. K is equals to V2 divided by V1 equals to N2 divided by N1. Now by using this relation we can find N2 is equals to N1 into V2 divided by V1. So here N1 is 32 into V2 is 3000 divided by 250. What is the value of N2? 32 into 3000 divided by 250. What is the value of N2?
$384, sir.
384. Wait for 1 second. So I have to check that. $3,000 divided by 250 into 32. Right. 384 tons. Now the first question is over, primary and secondary number of turns. Now we need to find the area of core. So for finding the area of core, you can use E1 equation or E2 equation. So I am using E1 equation. E1 is equals to 4.44 into F into BM A into N1. Now from this equation we need to find the A value. So A value you can write A is equals to E1 divided by 4.44, frequency is 50 Hz, and maximum flux density is 1.2, and number of turns in the primary is 32, and here E1 is 250 volts. For now find the area. 250 divided by 4.44, 50, 1.2 into 32. What is the value of A?
Zero point 029, sir.
So approximately 0.03. What is the units of area?
Meter square, sir.
Right. A is equals to 0.03 meters. So this is the way of finding the problems based on the EMF equation. So remember one thing, here you need to use the two equations. One is EMF equation and transformation ratio. Based on the two equations only, you can calculate whatever you need. Okay, so you have to use these two formulas. One is EMF equation and transformation ratio. So once again, I'm repeating this. K is equals to V2 divided by V1, N2 divided by N1, E2 divided by E1, and I1 divided by I2. So here current is inversely proportional to this remaining all top parameters, that is voltage, number of turns, and induced EMF. Now shall we do this second problem? So I'm going to read this. A single phase transformer has 400 primary turns. So its value N1 is equals to 400. Next, 1000 secondary turns. So N2 is equals to 1000. And the net cross sectional area of the core is 60 centimeters square. So how we can write 60 into 10 power minus 4, because centimeter is 10 power minus 2. So here centimeter square. So finally we obtain the area in terms of meter square. And next thing is frequency is 50 Hz. The supply value at 520 volts, and its input voltage V1 is equals to 520, and the peak value of maximum flux density in the core and voltage induced EMF in the secondary winding. So we need to find these two values. First of all, note down the given data. Now I already told you that the supply voltage is equals to E1. Okay, now V1 and induced EMF prime both are equal. So you can write E1 is equals to 520 volts. By using the transformation ratio, K is equals to N2 by N1. So N2 by N1. So already we have the number of turns, right? N2 by N1 means 1000 divided by 400. What is the value of K here? 1000 divided by 400.
2.5.
2.5. Now, from the same transformation ratio, we can write E2 divided by E1 is equals to K. Now, E2 we can write E2 equals to K into E1. Then you can calculate that what is the induced EMF in the secondary. So K is 2.5 and E1 is supply voltage is 520. 2.5 into 520. What is the value of E2?
$1,300.
1300. Okay, now, so E2 equals to 1300. So your question number 2 is over. Now the peak value of flux density in the core. Ante what is the value we need to find here? Flux density is Bm only, right? So for finding this value, we can use E1 as well as E2. So I am using the E1 equation. E1 is equals to 4.44 F Bm A into N1. This is the EMF equation on the primary. Now Bm is equals to, what is the E1 value here? 530, because supply voltage equals to induced EMF, divided by 4.44 into 50 into area of the core is 60 into 10 power minus 4, and number of turns in primary is 400. Then find the maximum flux density. What is the value of maximum flux density? What is the value of maximum flux density? Students, are you finding that value? So the value of maximum flux density is 0.976. What is the units of maximum flux density?
Weber per meter.
Right, Weber per meter square. So you will get questions based on the EMF equation like this. Okay, now. So because EMF equation eటువంటి problem వచ్చినా, you have to use these two equations. One is EMF equation of primary and secondary, that is E1 and E2, and transformation ratio. Okay, students, this is about today's class. In tomorrow class, we are going to discuss about how the transformer will be worked without load and with load in the terms of diagram, phasor diagram. మన ఫేజర్ డయాగ్రామ్ బేస్ చేసుకొని ట్రాన్స్ఫార్మర్ అనేది లోడ్ లేకుండా ఎలా వర్క్ అవుతుంది, లోడ్ ఉన్నప్పుడు ఎలా వర్క్ అవుతుంది. సో దట్ ఈస్ ద టాపిక్ we are going to discuss in tomorrow class. Okay students, I am going to end this class now. Thank you.